time people are modeling the code. Okay. You start the recording also? 1 second. Okay, yeah, well, let's start. So today, Linus, after publishing his papers, we will present about it. So thank you for coming, and the floor is yours.
Thank you, Sana. So I want to tell you today about fire string corrections from ODD. This is based on 3 papers, and the one that came out 2.5 years ago, the first one, and then the last paper came out about 2 weeks ago. So let's start with some very general motivation and setup where we're interested in what the question is and where we're interested. So in a quantum theory of gravity, we expect that the Einstein-Hilbert action will receive corrections. Think of it as an effective action. So we will have schematically something like this. Let's take the dimension to be arbitrary, or call it capital D. In 4 dimensions if you want. So later on, I'll be talking about string theory, it will be 26%. So we have the usual, we expect to have the usual Einstein-Hilbert action at very low energies, but then we expect to have corrections to this, which involve high powers of derivatives, become some coefficients called refer to C1. And we could have, for example, the square of the Riemann tensor that would have 4 derivatives, and for dimensional reasons, we would expect this to be suppressed by some dimensional parameter. We expect to be the finite. So naturally, you would expect C1 to be some order 1 number. And then you can have more of these. For example, you can have the next order, you can have C2, something involving the 3rd power of the Riemann tensor, for example. So let's just write one particular index structure. Of course, there's several ones that you can have. For example, you could have it like this. This would now have 6 derivatives. So we need the 4th there. And then you can have many more corrections. But we would be interested in knowing these numbers for applications, for example, to black holes. We want to give corrections to black hole entropy or something like that. We need to know those coefficients.
Is there a blank mass in front of the whole thing?
Yeah, there will be some dimensional parameters. Right, so we're interested in this coefficient C9. But we can't compute them from Einstein's theory itself. We need a theory of quantum gravity to be able to compute these coefficients. And in fact, there's only one theory where we know how to compute this. On string theory.
But I guess you could sort of, in some cases, constrain them by imposing additional.
Yeah, because it's constrained them by symmetries, things like that. But if you want to actually compute them, there is only one setting where we know how to compute them, even in principle, and that's the string. course, we don't really know how to compute them in 4 dimensions in string theory yet, because we don't have the compactification that gives us our 4-dimensional universe, but that's a different story. In string theory, we know, at least in principle, how to compute any number of these coefficients that we like. It was complicated. We know how to. So if we want to talk about these coefficients, we have to string theory. So how does this problem look in string theory? Well, in string theory, the low energy effective action takes the form of a double expansion. String theory takes this form as effective is a sum over 2 integers, so k and l, from 0 to infinity. Explain what this means shortly. GS over k minus 1, alpha prime for l, and s. Okay, so it's a double expansion, and it's two things, GS and alpha prime, and as you know, GS is extreme coupling. The expectation value equal to pi. Pi is the scale of field called the dilaton. And this is the parameter that controls the stream loop expansion, stream genus expansion. And then the other parameter entry here is alpha prime, which is essentially the inverse string length. So it measures some of the stringiness. So how much it deviates from the particle case corresponding to alpha prime 0. Okay, so we have an expansion of these two things. But for this talk in these papers, I will not consider the GS corrections. The higher string corrections will not be considered, so I will take only the case k is 0 in the sum. But we will consider the alpha prime corrections. So taking k is 0 corresponds to being at tree level in string theory. So we don't include any string loop corrections. But there's still an infinite series of high derivative corrections that we have to deal with. Okay, so if we do this, now the effective action, let's call it S3, emphasize that we're field level effective action, take this form. You should measure the d-dimensional space. Of course, D will have to be the critical dimension of the string theory, so it'll be 26 for the bosonic string and 10 for the superstring. E to the minus 2 pi, which comes from the fact that if k equals 0 here, there's the contribution here, which is GS minus 2. And then we have the expansion in alpha prime. We can write this as L 0 plus alpha prime plus alpha prime square L2. Okay, then I'll simplify things even a little bit more by restricting to the massless fields that are common to all string theories. Well, first of all, I restrict to the massless fields, but not all the massless fields, just the ones that appear in all the string theories. We're talking about closed string theory, by the way, because we want gravity. Okay, so what's there something called an SNS sector field? It exists of the metric. First, because we're interested in gravity. That's going to be most interesting. But then there's an antisymmetric two form called the B field. Okay, the metric is the first symmetric, and then this is that B has two indices for the antisymmetric. And then there's a dilaton that we already encountered. Scalar field. Now the metric is of course a gauge field. Components of the metric are physical. Similarly, the B field is a gauge field. So what will appear in effective action has to be manifestly gauge invariant. By the field strength, so in the case of the metric, that's the curvature Riemann tensor. And in the case of the B field, it's the field strength of B. Which is usually called A. So and we'll symmetrize here. And a lot of the field strength and electromagnets. One extra index. Okay. Now let's begin the lowest order, zeroth order in alpha prime. The L0 takes the following form. The conform, which is just the rigid scalar, we would expect, because we expect to recover Einstein-Hilbert action on the fields. But then there's kinetic terms for the other fields. The kinetic term for the dilaton is then 4. And then the kinetic term for the B field. Yes, threshold of the square of the field strength minus 112 times. Okay? This is, of course, very well known. This is low energy effective action for the bosonic string, but the same terms also appear for the superstrings, but in those cases, there are also additional fields present. But now we'll restrict only to these fields. So this part of the action is common to all string theories. Okay, so this is all very well known, but we're interested in this high derivative alpha prime, specifically corrections, L1, L2, and so on. So how do we find these? Well, the standard way to compute the high derivative corrections is to calculate string scattering amplitude. Another way to compute L1, L2, and so on. In this case, tree level, because you're restricting the tree level. String scattering. Okay, so, well, of course, to get the Lagrange and the action, first you can get the scattering amplitudes, and then you have to match, so you have to make an ansatz for the effective action, and you have to match that the amplitudes coming from that effective action to the amplitudes that you computed from screen. So that's how it's done. It involves two steps. You have to do the scattering amplitude, and then you have to match it to an effective action. Okay, and for the first correction, this was done quite a long time ago. It was found by Simon cycling. Six. Completed the first correction. They found that it involves something that looks like the first time I wrote that the Riemann tensor squared. Okay, and then there are some other terms which I'll, for the moment, describe schematically. They involve the square of the field string B times the Riemann tensor, and then there's a term that involves the fourth part of B. Okay, you'll notice that there are no autopowers of the B field. That's because there's a symmetry, the bosonic string sending B to minus. So H will only appear in even powers. So these are all the terms that are allowed and they will appear. Disorder. In fact, so this is true for both the bosonic string and the hydraulic string. The form of the direction looks essentially the same, but there's some different coefficients in the hydraulic case. I will not talk much about the hydraulic case here because it's slightly more complicated because it involves modifying the gauge transformations at higher order because of the Bridgeworth's anomaly cancellation mechanism. So what I would say will mainly be relevant for the bosonic string, which is less interesting, but it will also be relevant for the and at the net sector of the type 2 string, something you're interested in. Okay, so this is the first correction. So it was computed completely with scattering amplitudes by these guys a long time ago. What about higher corrections? Let's look at the next two words. So second order non-primary L2. Turns out to involve the Riemann tensor Q. Like a bunch of other stuff. And at the third order non-prime, we'll get, and not surprisingly, the Riemann tensor for the fourth power. But what's a little bit funny is you find a strange coefficient here. It's say that 3. So let's say it's the Riemann second function. Plus other terms. Ones that involve H. In fact, these terms, in both cases, these terms have not been fully computed from scattering amplitudes. We only have incomplete information about these. From string scattering amplitudes. The terms involving the Riemann tensor. No. Okay, strictly speaking, this is for the bosonic string. For the heterodic string, there's a similar direction, but it doesn't involve the Riemann tensor. It doesn't involve the cube of the Riemann tensor. It involves the Riemann tensor and some Lorentz transcendence. Let me not talk about the bosonic, about the heterodic string. So for the bosonic string, you have this first alpha prime direction and the second alpha prime direction. Whereas the first direction that appears from the type 2 string, maximally supersymmetric string, is this direction in third order. In fact, it has been shown to appear in all theory theories, the coefficients. So it appears in the bosonic string, the heterodic string, and also the type 2 string. Okay. So this direction is very interesting because it's fundamental string theories. But we will also be interested in this correction because it's simpler. We can learn something looking at it, even though it's only, we're not ultimately interested in the bosonic string. We can still learn something by looking at the corrections in that case.
So this has been computed from scattering amplitudes.
Yeah, the structure of the Riemann tensor here and here, that's been computed from scattering amplitudes. But these other terms, as I said, some of them have been found from scattering amplitudes.
Where does the zeta function come from in the scattering amplitude? Some or something different?
I'm not sure off the top of my head.
And what about the first order correction for type 2? Type 2, so you wrote that that's bosonic and heterodic, but in type 2,
there's no correction.
There's no correction.
So the symmetry forbids this correction in the case of maximum symmetry, the correction.
Excuse me, sir. Am I audible? It is not exactly clear to me how scattering amplitude can be useful to compute the corrections. I mean, what's the exact procedure? If you can tell me again.
Well, you can get the scattering amplitude in string theory. So this is for computing three-level scattering amplitudes in string theory. Right? Put operators on the sphere and you compute the amplitude. And then you match that amplitude, then you make an ansatz for an effective action. You can use that effective action to compute the scattering amplitude. And then you match, you ask that they agree. And that gives you the effective action that reproduces by construction the amplitudes that you get from string theory.
Okay. Thank you.
So the idea is to have an action that reproduces all the scattering amplitudes that you get from string theory. Up to some order, obviously, you have to solve some. Okay, any other questions?
So I know that in scattering community, people are talking about symbols of amplitude, and their zeta functions and pi and so on have some order, and it's actually I mean, there's some kind of deep mathematical reason why zeta function appears in scattering amplitudes in this. Has this been related to that in this case? Do you know what I'm talking about?
Yeah, I know this transcendentality, so you can organize the answer according to the transcendentality. I'm not sure actually how it's connected with this. I think, I mean, here it doesn't, here, if you do the calculation from the field theory, you don't get this. It comes from the string calculation. So it's a little bit different. It's not from the usual Feynman diagram calculation. This is coming from the string. So I assume it comes from an integral to there. I don't remember exactly how it comes out. It comes out, but in the effective action, it will just appear as a factory printed as a string. Right. So these were also computed in the 80s. This was again computed by Winside and Cyclin. '87, I think. And this correction, for the case of type 2, it was computed by Groth and Whitman. And in the heterodic case by Groth and Sloan. Again, around the same time, 86 or 87. Okay. But there's a reason that we only have incomplete information about these other terms, and that's that doing it this way, calculating the scattering amplitudes, quickly becomes complicated. For example, to find all the terms here in this fraction, you have to go up to 8 points. We can compute up to the 8-point tree level string scattering amplitude, which is something that's not been done. And not only do you have to do that, you have to make some enormous ansatz for the effective action. You all write all the possible terms in the effective action and match it to that amplitude. Both parts of that calculation are quite complicated, and they're not figured out.
Sir, for L1, what point amplitude did they use to fix this L1?
Well, for this 3 points, and therefore
L1, the first correction.
already been on sense.
Even that one, L1.
Yeah, like I don't know.
Well, to fix all the terms, you have to go up to 4 points here, because there's a 4 points. So 3 and 4 point, I think, will suffice to fix.
I see. Okay.
What about the dilaton? You put it constant or?
No. Good. There's no dilaton.
No dilaton at all.
You could imagine having a term involving the derivative of the dilaton,
Right.
but it doesn't appear. So the dilaton only appears as this overall factor e to the minus.
It never appears, or it just?
Actually, whether they, no, I'm not 100% sure whether they included the dilaton in this scattering amplitude calculation. But it would be true that it doesn't. I think they did, but I'm not 100% sure. It turns out it doesn't.
Why?
Not in the second, not in the third. Order.
Well, as I said here, we have from scanning amplitude, we have incomplete information here. So from the scanning amplitude point of view, we don't know. But I will tell you some more things about what we know.
I mean, naively, you would think that computing amplitude with a scalar field is not simply in
Yeah, in many calculations, the delta cone is not included. I'm not exactly sure why. I might be some technical reason for people are less interested in terms. Of course, there are many ways that you can manipulate the action. If I integrate some term by parts, I will generate terms with the derivatives of the delta because I have this factor minus 2 in front. So I'm writing the action in some particular way of writing. Because here there's not really anything I can do. I want to keep it K2 variant, but in other cases, I have terms with explicit derivatives that I could integrate by parts, produce other terms. So the form of this Lagrangian is not unambiguous by any means. There are lots of ways to rewrite it using integration by parts and the Yankee identities, for example. And another thing that you can do are field definitions. So there's lots of ambiguity coming from those, from the freedom to do that. Which I did fix somehow. Right, so as I said, the amplitude calculations become very complicated if you want to fix. Even fixing all these terms in second order now has not been done using amplitude calculations. You have to go up to 6 points. Because it could be done, but it hasn't been done, and here it's worse. But still, we would like to find the full form of it. We would like to find what corresponds to these terms here. So we can ask if there's another way to do it, other than computing them correctly from setting amplitudes, and there are ways to do it. Quite muted for a long time. One is probably the most common, although it's used for symmetry. Of course, this would only work for the superstring, so that it will not help us for the bosonic string, where we don't have supersymmetry. But for the superstrings, you could, if you know the first term, you know the whatever Riemann tensor Q, Riemann tensor to the fourth power, you can try to supersymmetrize it, and presumably that will uniquely fix all the other terms. That's the idea, and people have tried to do this, but again, no one's been able to find all the terms using that approach because again, it becomes very complicated.
At the same order, so L2 by itself.
Yeah, you can try to supersymmetrize. You start with the Riemann cube term and you try to make it supersymmetric. Sorry, in that case, it doesn't make sense because that correction is only there for the bosonic string. So it will not be possible to make it supersymmetric. There's a corresponding correction for the heterotic string, which does not involve the Riemann tensor cube, but involves some Lorentz-Simons term that you can supersymmetrize. And yeah, in that case, it's known how to do that. But that also involves some other trick. There was some work by Berkshire and Rose and Hayes when they did that. But this third correction, we went to the fourth. You can also try to supersymmetrize it for you. But there's still very incomplete information from that. There's some partial results.
Does the supersymmetry method find the zeta 3 or like it's just
No. This doesn't fix the overall coefficient. So the overall coefficient will be arbitrary, but it will fix the relative coefficient between all the terms, presumably, if you have enough supersymmetry.
So if I also include some fermions, it also has some zeta 3 in front as
Yeah,
well.
everything will have an overall state. Right, so this how this works for type 2 and heteronic. It does not tell us anything about the Platonic string. Of course, we're less interested in the Platonic string, but if we nevertheless want to find the corrections for the Platonic string, we can now use symmetry. There's one other approach which works for all of them, and that's to try to use duality symmetry. And that's what I want to talk about today. Okay, so can we use dualities somehow to fix, let's say we know the first term, we do it from the scattering amplitudes, can we fix the other terms? By using, we know the string theory has a bunch of dualities, can we use them to fix all the other terms? The short answer is yes, at least in those two cases. In fact, in a series of papers, Mohammed Darusi has been able to fix all those dot terms. For L2 and L3, second and third correction on prime, growth by using T duality. These papers go back to some 2018 or something, detailed now, it's a bunch of papers. Okay, so what's the approach? Well, the idea is the following. First step is to start from the most general possible ansatz in d dimensions. General ansatz for the effective actions, you have to write all the Gaussian variant terms. So we're combining all using the Riemann tensor and H and derivatives of the dilaton. Right? Already, this is quite non-trivial because in the case of alpha prime cube, that involves some 1,000 terms in 10 dimensions. It doesn't matter really what the dimensions, it could be arbitrary, but essentially we're interested in these 26 or 10. Okay, so already from that you can see that you have to implement this on a computer. There's no way you're going to write down all 1,000 terms into this document. So this was all done on a computer. Some symbolic algebra packages, which you can just easily enumerate relatively easily. Enumerate all the possible terms to take the most general effective action. The most general answers for the effective action. Okay, that's only step one. Then step two is to reduce this on a circle. Right, so start from some arbitrary d-dimensional manifold and use reduce it to some d-1 dimensional manifold on the circle. We assume there's no dependence on the circle. So it's just dimensional reduction.
So that has to be an isometry. So,
Yeah.
so you assume that there is an isometry in the backup. Could it be terms in the predictive action that vanish when there's an isometry that you don't see?
Some terms will vanish.
I mean, what I'm asking is there something that you might miss using this method because
Yeah.
since there's an estimate.
Well, in this case, you don't miss anything, but you can take a more extreme case. Let's say you can reduce it just to one dimension, just to time. There's one of those spatial directions. That's what people did. I'll come back to that. Early on, people did that called the cosmological reduction because they're interested. That gives you some kind of cosmology, just depends on time. In that case, a lot of things vanish. You get incomplete information if you try to. If you try to use that, it turns out you cannot then use dualities to fix completely the form of the higher dimensional function. In this case, you can, it turns out. It's not obvious to start with. Okay, so you take the general effective action, you reduce it on S1. 3, you require the result to be invariant in T level.
Yeah, okay, so I understand. So you write down all the terms not assuming any isometry. Then you assume an isometry, reduce. But you still see that you can fix all the coefficients of the other.
Yeah. Okay, and he showed that this uniquely fixes the, again, uniquely up to all the stuff you can do, integrate by parts, use Bianchi identities, doing fielder definitions. Up to that, it uniquely fixes the answer in 10 or 26 dimensions. Okay, so it seems we're done. Solve the talk here. Of course, we're not done. Because the problem, well, of course, it's very nice to show that the uniquely fixes the answer, but the answer that you get is not very useful. Remember, we started from nonsense for alpha prime cube around 1,000 terms. And in fact, we find that a lot of these terms have to be non-zero. And the simplest answer that Eris is able to write for the alpha prime cube result of 3 has about 200 terms. So it's better than 1,000, but it's still too much to work with. You can't really do much with the Lagrange, which is 200 terms. I have, unless you can put it on the computer. It's not very satisfactory, at least if you believe that there should be some simpler structure underlying. I mean, the first correction you have is quite reasonable. In fact, if you can write it, we'll see, you can write it as only 3 terms. But there are 200 terms of the prime cube to be useful. And so we would expect, there are certain reasons to expect that the answer has some sort of reasonable structure. It's not completely random. But it's extremely hard from this expression of 200 terms to see any structure. It just, the terms kind of appear with more or less random coefficients. It's very hard to read anything. And there's so many ways to rewrite the answer. It's almost impossible to extract what the right structures are just from that answer. we expect symmetry, but it's very hard to find it from this result. Just because there's so many terms to start with, and there's so many ways to rewrite them. It's almost impossible. Okay, so
Can I ask something?
yeah,
So, you know, there has to be some number of coefficients that you need to fix from the scattering amplitude calculation. Right, it can't be just everything, just the overall coefficient is not fixed. So how many coefficients do you need to fix to really fix all the coefficients?
I think it's just the overall coefficient.
So
I mean, possibly you have to fix one term, but I think it's just the overall coefficient.
So for each terminal of prime, there's only one unknown, essentially, that is not given by this method that you need to fix.
Yeah, actually, it's not even that, because it turns out that the first and second alpha prime correction are non-independent, so they have one coefficient. So actually, up to this order, there's only two coefficients that you have to fix from some other input, if you use this video alpha approach. Okay, so because of this, we're interested in trying to find some reasonable structure, if it exists. There's some reason to think that it does. And for this reason, we want to use some different approach, because the problem here is that we're relying on a computer, and you make some ansatz, but depending on how you take the ansatz and how you extract the result, the answers will differ wildly, and it's very hard you don't have any insight into what's going on in the intermediate steps in the calculation, because that's done on the computer. So you don't really know how you should structure the result at each step. So we want to do something where we don't rely on a computer, where we can recognize some kind of structure. So we will take a different approach, which is still closely related. Which uses ODG symmetry, which I will explain now. Okay, so this was a long introduction. The outline will be something like this. First, I will explain what this ODG symmetry is. Then we'll see how the area of dimensional reduction. And then we'll talk about the corrections. So the first one is alpha prime 3 months squared, and then we have alpha prime squared 3 months cubed, and then the one we're most interested in, the alpha prime cubed. And then fourth, okay, we'll see how far we get. I'll try to tell you something about this result, at least. Okay, let's first talk about what this ODE symmetry is. So we'll consider the dimensional reduction. But now to not do like Euclidean and consider the dimensional reduction just on a circle, we'll reduce on an arbitrary number of dimensions. So we will reduce from capital D dimensions to capital D minus little d. So we will reduce on small d number of dimensions. Okay, so in Garusi's case, this little d was 1. Okay, and again, this is dimensional reductions. We just take all the fields independent of the d, the small d number of coordinates. So let's hold on. Y, these are prime for these coordinates. So this will be in compactification, these are called internal directions. So y and prime will denote these coordinates and y the c. They will all be spatial coordinates, of course. So we'll take all the fields to be independent of this y and prime. And the remarkable thing that happens when we do this is that an OD, D symmetry appears. But it's the same little d, the number of directions we reduce on. We get a symmetry that is rotation in a space that has twice the dimension. Right, this was realized originally by Meissner and Tiano. Early 90s. And then analyzing and improving on the development side. So why does this symmetry arise? Well, first, it turns out that really the non-trivial part of the symmetry is just OD times OD. Of course, OD times OD is a subgroup of OD times D, and that's really the non-trivial part of the symmetry. Okay, because it turns out that the rest of ODD is made up by gauge transformations. So that's sort of trivial, whereas this OD times OD subgroup, it's not. So where does it come from? Well, roughly this, this symmetry is special to string theory, and essentially comes from the fact that the string has left and right movers. So with closed strings, it's left and right moving nodes. So this symmetry arises to, because in this case, and maybe when we're reducing on these d dimensions, we're dropping all the dependence on these coordinates. which is like restricting to the zero momentum sector of these coordinates. From left and right moving. Close in. So, in general, we can expand the coordinates. The coordinate solves and wave equation. Look at these internal coordinates, solve the wave equation on the string, and the general solution is given by the right moving piece and the left moving piece. What things to do, we number the string, we realize that that's the solution. But now what happens in this case is that these become effectively independent. And it turns out that you can actually rotate each with a separate OB, rotate with separate OB rotations. Naively, if you only have the diagonal, you rotate both the same way. This is the only thing that would preserve this writing. But actually, it turns out that when you write the correlation function in this theory, you actually have a separate symmetry in the right moving and the left moving sectors. You can independently rotate the right movers and the left movers. So this doubles your symmetry. And you do that in something very stringy. Because it came from the left numbers. And what's then shown in this paper is that this symmetry actually persists to all orders in alpha So when we're interested in three-level effective action, we can use the symmetry, which should be there at tree level. All is not.
Sir,
Yes.
In this in the context of right moving and left moving modes, how do we understand this trivial part of the ODD symmetry? I mean, where is the trivial part here?
How do we understand which part?
The trivial part. The non-trivial, I understand it's the OD rotation of each R and L modes.
You mean the rest? The rest is to do with reparameterizations, for example.
Reparameterizations in sigma and T, or what?
Diffeomorphisms, if you want, right? You can perform diffeomorphisms, and that will and you can show that it actually generates the rest. Basically, diffeomorphisms together with some shift in the dialecton, but that you can generate all the rest of ODD. That's also explained in sense paper.
Okay, thank you.
Okay, let's see. Okay, so we still have this symmetry. I didn't quite prove it, I just gave the plausibility argument of this symmetry is here, but the argument is not very long. You can find it, it's like half a page in the sense paper. It's formulated in string field theory, but you can also formulate it in other ways. So, but we're not interested in how the symmetry acts on the left and right movers. From the point of view of the space-time effective action, we're interested in how it acts on the fields, the party space fields. So the question is how the symmetry is realized in the fields in the torus space. Okay, so that's the first thing we can answer. We want to be able to use this symmetry to constrain some other form of effective action. So we have to look at what happens to these fields in dimensional reduction. In the dimensional reduction, the metric, we put an underline to emphasize that it's higher dimensional metric I'm talking about now. So 10 or 26 dimensional metric. When we dimensionally reduce the metric, each index can belong either to the external directions that we didn't reduce, or it can be one of these prime internal directions. So we will get a metric in external directions, we will get something where one index is external and one is internal, and prime. Okay, and this will look from the external point of view, this will look like a vector field, so we'll call it A. Because there's like one space-time index of the reduced theory, and then it has an internal prime index. So there will be a collection of this. In fact, there will be D of them. Because the prime index is obvious. Remember, all these are just depending on X, there's no dependence on the Y. Assumption, and then for we have two internal indices. And from the external space-time point of view, that just looks like a bunch of scalars. It's the usual collusive line reduction if you want of the metric, and then we can do the same for the B field. Well, it's exactly the same. The only difference is the indices are anti-symmetric here, and you will get a B field in lower dimensional theory. You will get something which is one external and one internal index. Which again will give you vectors. I have to distinguish the two, so I will put one here and I will put two here. So see, we get two sets of D vectors from the external space point of view. And then again, we can have D and prime, which again looks like a bunch of scalars. And finally, the dileton doesn't have any indices, so it gives me another scalar. The lower dimension. Okay, so what do we get now in the reduced theory? Well, we get the same as we had in the original theory, which is this the metric B field and phi. But besides that, we get two sets of vectors and a bunch of scalars. We get 2D vectors, where D is the number of dimensions that we reduce on. So if we reduce on a circle, we get two vectors. But we're keeping this D general. A1, A2. Suppress the external index.
So it's not in that.
Oh,
Yeah,
as well as some scalars. If you add them up, this is a symmetric matrix, this is an anti-symmetric matrix, and they add up to an arbitrary matrix, you get these squared scalars. Well, from the metric in. Oh, that's already put it. Okay, and now we want to ask, there should be an ODD symmetry here. How is it acting on these fields? You see that we arrange them in particular form. We arrange the vectors into a 2D vector, so we just put them together. But A1 and A2, remember A1 comes from the metric, A2 from the B field. They have an external index M. Then they have an internal index, which was M prime, which I'll put upstairs here and downstairs here. For conventional reasons. So I group them together, that. And the others, the scalars, so those are the vectors, and the scalars. We group into a 2D by 2D matrix. Okay, so the 2D vector and the 2D by 2D matrix, which sometimes calls image. Like this. Prime. Right, so G with upper indices as usual would be the inverse metric in these internal directions. And finally here, G times minus E. Okay, but the contraction is zero, which all these one index is contracted with the inverse metric here and here, and here it's the inverse metric. Okay, so you can, obviously this is something you can do at this point, it's not all required as a suitable, but of course we can arrange things like this if you want to. And the reason this is useful is it turns out that ODD acts simply on these objects. ODD, I want to call this, I call this curly H, and call this a curly A. And I introduce this capital letter index, capital M here, which runs over upper and lower internal indices. This is just imagine, but it turns out to be useful.
So shouldn't it be capital curly A, little n, capital N?
Yes, there should be a little n. Just for the external space. Okay, so The point is now that OBD acts on this capital. So this is the capital image runs over 2D value. The upper one and the lower ones. And remember that OBD acts on this guy like this. So this forms an ODD vector, whereas this forms symmetric ODD tensor. So O here is an element of ODD.
Go back to your statement before that the off-diagonal pieces of the ODD is just gauge transformation corresponding to what was the diffeomorphisms. You know, if I look at what the diffeomorphisms would do and reduce, so I skip the internal coordinates, then the A's just transform as U1 gauge transformation under what used to be diffeomorphisms before. Right, it's D, M, psi, M prime.
Yeah.
And the other one drops out
Right.
because there is no.
Diffeomorphisms and become gauge transformations of this vector.
Right. But
Well,
how
the
do
diffeomorphisms become gauge transformation of this, or B fields, some of the B field gauge transformations become the gauge transformation of the
oh, yeah, okay, because it's the B field.
It has both.
Right, right. But they both transform
Yeah.
as gauge.
U1 gauge as well.
Now, how, and then you said, how, you know, if I just look at the off-diagonal pieces of ODD, I'm just mixing A with A1 with A2. So how can I see that those things are really the same? Or somehow correspond to each other? I mean, you said.
They're not the same, but there's a symmetry. It turns out this is a symmetry of the theory. So there is a symmetry under mixing these with each other. It's not obvious why it should be there. Right? From the high dimensional point of view, it looks very good. One came from the metric, one came from the leaf. Why should you mix them? But we know that T duality mixes the metric and the leaf. Right. So there should be some symmetry that mixes them. And in fact, this ODD symmetry is very closely connected to T duality. It is essentially the realization of T duality.
I'm just trying to understand what you said before, that it's the diagonal pieces of ODD that are interesting. Off diagonal are essentially gauge transformations corresponding to diffeomorphism. So
yeah, I don't think it's obvious here because it will not act in the same way here. I don't think. I think with this choice of coordinates, it will not be true. I think that just one OD factor will rotate this and the other will rotate that. It will be something more complicated. But you can go to of course a normal basis where that would be the case. But then they will be the fields that are rotated by one single OD factor will be linear combinations. And we'll do that shortly. But this is not the same decomposition as this OD tensor to be.
I see. So the matrix.
So they, by one of those OD factors will still mix these two.
Okay, so somehow this is not sort of the fundamental representation of ODD, what I would do.
Yeah, this is not the best way of writing it.
Yeah.
But, okay. For now, we just like the coordinate indices, but yeah, the point is that these objects transform nicely into ODDs. If you collect them in this way, this is how the ODD symmetry is realized. So now we know how ODD acts on the space-time fields. That's the point. So that's something that we can use in the effective action. But if you want to include all these fields, it's quite complicated because now you have these vectors, but you also have all the scalars, and there's quite a lot of right. But actually, it turns out that you can simplify your life and only consider some terms. And in fact, we will only look at the vectors and we'll just forget about the scalars involved. So we will only consider terms involving vectors. We'll turn out that that will be enough for us, as we can see. Okay, so now we have to think about how these. Well, what I didn't say is ODD does not act on the other fields. So the reduced GB and phi without prime indices will not transform under ODD. So it's just that ODD just transforms the internal prime indices. Right, but we want to talk about what the Lagrangian is allowed to have now that we import this ODD. And we want to look at the vectors specifically. Now, of course, in the Lagrangian, all the indices have to be contracted. We can't have any free indices. So in particular, the internal indices have to be contracted. Because the vectors have one internal index, so that has to be compacted with another internal index. But there's only one object, which is one internal index, which is another vector. And contract it with a scalar, then you have one leftover internal index. Eventually, you have to contract it with another vector. So that shows that only even powers of these vectors can appear in the Lagrangian. Now I have even powers. And we will simplify even further and consider only the quadratic terms. Only terms that involve a squared, so terms quadratic in these two vectors.
Right. I guess if you say even power, then it can only be all inner products.
Well, I'm only talking about the internal indices, so because the external indices can be contracted in some other way.
Right. Okay.
It's just very thematic, but there will be terms that have, of course, there will be terms that contain no vectors. And because we're ignoring the scalars, those would automatically be ODD vectors, because they just contain fields that don't transform anymore. And then there will be these terms that are quadratic, those are the ones we look at. Then there will be things that have 4 powers of A, but we'll just forget about it.
Could be D power of A contracted with an epsilon. Or now 2D power. Oh, again is zero. So it doesn't.
Yeah.
So it has to be 2D. So it's
Yeah, but you, I mean, apart from the epsilon symbol, then all of the other ones, I guess, have to be inner products in the
Right.
in internal. I mean, the prime in this the internal.
Okay, so we have A1 and A2. So there are 2 of them. So we can form 3 different inner products of these. Guess we can get A1, some external index, which I don't care about for now, and I can contract the internal index with another A1, for example. I can do the same with 2. And finally,
what do you need a metric or something?
the metric is just delta. Well,
Well, I mean, we have G, this guy.
Yeah, before, there's this metric.
Right.
But I'm setting all the scalars to 0, so I will just take this to be delta. Because this is the delta plus something there. Okay, but we can talk about before we set the scalars to 0, then you can contract them with this. So the dollar just means a contraction of the internal indices. It could be an internal metric if you want, for now. That just means that it involves just the scalars, but eventually we will set those to 0. Okay, so the point is I can write three terms. These can all appear and will appear in the reduced effective action. But now comes the important point. There are only two ODD invariants. Right? Because to write an ODD invariant, I have to use this curly A object, this object. So I can use this, for example, to contract. So I have to use this ODD vector AM. And it turns out that there are two metrics that you can use to contract it. There's an ODD invariant metric, which we call AM. And there's this metric, which I can also use. But these are the only two objects that I can write that are ODD invariant. Okay, I should say what this is. This is the ODD metric, which is just ones off the diagonal. Again, we use off the diagonal. Once.
And the H within this is up.
The H within this is up will be this H contracted with two of these. So we raise the indices, we raise lower indices. Okay, those are the things that manifest the ODD invariant because of these transformations, and the fact that ODD by definition preserves split signature. And those are the only invariants that I can write. What's your base? Okay, but now you see there's a discrepancy. I could write three of these terms, but I can only write two invariants. So there will be some combination that's not compatible with ODD. And that's the point.
Okay, so here you can see the basis is different because the split signature electrically. If you have the basis that I was thinking of, it would be 1 minus 1.
Yeah.
And now you can see that you're sort of like
Right, you make some, but you take linear combinations. This we'll do very shortly, but no. Well, metric. Yeah, okay, good. So let's take linear combinations of A1 and A2. So, I'll say, let me suppress the indices, not for some conventional reason, there's a minus sign here. Not important, it's just to agree with some conventions. So essentially, I take 1/2 the sum of the two, and I take 1/2 the difference. There's some extra minus sign there. It's not annoying conventional reason. So we 1/2 times it. So let's introduce those two linear combinations, A and A hat. Some things become simpler, close to those. It turns out then that A squared, we just contract internally with the dot. And write it like this without indicity. Maybe I should be more careful on writing it. Yeah. A hat. Those are the two ODD variants for a linear combination of ODD. Those are fine, those are compatible. Since one manifesting variant in the ODD, while the other, the inner product of A with A hat, the product between these two, cannot be ODD rank because to the one is ODD rank. In fact, it violates ODD explicitly. And this goes back to your comments of this A will be rotating under one copy of D, so the inner product is always invariant. The A hat will rotate under the other copy, so the inner product is invariant. If you take the inner product of the two, this is rotating into one OD and that's rotating under the other. So this phenomenon explicitly breaks OD tax OD. So, okay, so this is the key observation that we use. Because these things, these sort of combinations will appear when you do the dimensional reduction, but the necessary condition for ODD symmetry is that all such terms have to cancel out because they explicitly break ODD. There's no way that they can be there. And we know that ODD symmetry has to be there because it's sans orthogonal. So the necessary condition is that all such terms have to cancel out. In the reduced action. Actually, it turns out they're not. Now, correctly, you will have to do a bunch of integration by parts or by total derivatives, and it turns out also field definitions will come right. Okay, but the point is that already this condition, which is this is just the necessary condition for ODD. It's not the sufficient condition, but it turns out to be extremely strong. It essentially fixes everything. Essentially fixes already just this condition essentially fixes that. It fixes the form of the action almost completely. It's a very small it's a very small subset of terms that it turns out it doesn't fix, but they will not be very important for us. But the point is now that this is much easier to implement just looking at these terms, this is a very small subset that we generate in the dimensional reduction. Just looking at these terms and asking that they cancel out is much more simple than looking at all the terms. So this is something that you can hope to do by hand. Much simpler than requiring the full complete. Even for the equals 1, which was essentially the case considered by Gaussian. Already spent a lot of time. Try to speed up. So now we can carry out the dimensional reduction, but we don't want to keep all the terms. We're only interested in these terms. So that simplifies things. Otherwise, it's just a standard cosine reduction. We're just keeping some terms. So we're setting the scalar to 0. So we need the reduction of the field strengths that appear in the actions. We need the reduction of the field strength of B, which is H, and the Riemann tensor, and it involves a spin connection. So we needed to predict Riemann constraint. H turns out to be a lower dimensional H, essentially, up to shift by some terms. So I put a half on here to denote the fact that it's not just the field strength of B, now it's shifted by some, essentially a Chern-Simons term involving the gauge field. So that is not important for us because it the shift with respect to OBD symmetry. This was under OBD. But we can also have component with one internal index, and that turns out to give minus f we see prime. But this is the field strength of the A that we find. Okay, and of course, with the reduced action, the gauge field themselves will not appear because of gauge invariance, only the field strength here. Okay. It's sort of obvious you have to get this combination because in this combination, the A1, the F1 piece will cancel out, it will just be a piece of the B field, which is and then you do a spin connection. All the indices are external, you just get the spin connection in the reduced theory. But you can also have one index internal. First index is internal. You get one pass. First index is internal, or if the one of the The last three, this is internal. The last one, you get the same up to signs, you get that cutout. Right, so the relatively simple well, H and spin connection just gives me essentially the field strength of those combinations of field strength that will define H fields.
You're not assuming torsion, putting torsion into the connection.
No, this is the ordinary connection, but now I will consider a torsionable connection. Yeah, well, first, the dilaton doesn't do anything, because it's going to stay with the dilaton just. Gauge fields. But we need the reduction of the Riemann tensor. And now it turns out that it's better not to work with the Riemann tensor, but to work with the Riemann tensor that's computed from a torsionable connection. Because it behaves more nicely under developments. And so further, really sure. Torsionable connection. Which, well, you can define here, different point of this minus. That's the standard string connection shifted by plus or minus 1/2. Which H also has 3 indices. So I can add it, the factor from the string connection this way, and doing that gives me a string connection with torsion. The torsion is controlled by this. And so this gives me a torsionable string connection. And I can work with either plus or minus because ultimately I have a symmetry under changing the sign of the G here, so it doesn't matter which one I work. So if you compute the curvature of that connection, or the torsion for Riemann tensor of that, take the following form. I would call it curly line. I will take again just take one choice, and for some conventional reasons, pick the minus sign, but then give the curvature of the minus. So I call it curly line, but I can always rewrite it in terms of omega plus instead. If you compute that, you find the neutral Riemann tensor minus determine the derivative of H plus another term quadratic in H. I mean, that's sort of obvious from my views. Okay. And what does this mean? So I'm defining H squared with 4 indices. This would be 2 H's with 1 index contracted. And so that's what's entering there. And then this is equal to that with an anti-symmetry in the first 2 indices. So this Riemann tensor is again anti-symmetric in the first 2 and in the last 2 indices. Automatically, but it will not have the symmetry under exchanging the pairs of indices. This is symmetric. This is actually anti-symmetric under exchanging the pairs of indices. Let's fall from the anti-symmetry. Okay, that's again symmetric under exchanging the 2 pairs. Okay, and then finally, if you like the course climate reduction. Again, we're only interested in the terms quadratic in the gauge field. So for this torsional Riemann tensor, I'm following with an R hat, which is just the usual one, again shifted by something quadratic in the gauge field, but which respects the ODE symmetry, so I don't care about it. But we get one more term here, which is f at the okay. This term is not compatible with ODE. It's explicitly very common. So that term is very important for us, because it has to cancel out in the end. Okay? It's very short. It has a conjunction of the habit on the end. And then you can have one terminal index. And what turns out to be just a derivative of n, which is strength. But now it's a derivative with this connection on the minus. I put the minus on the derivative. It's also very important. And then there's also another one because there's no symmetry in the two, exchanging the first two and last two indices. This thing is different, and it will be 9 plus. Okay, now half appears here and half appears. And that is about the relevant components which we don't need. Because the only complicated things that those 4H, for example, which we're dropping. Okay, so this is all we need from the dimensional reduction. We add this, and the reduction of the Riemann tensor. And now, basically, because of this, from the reduction of the dilaton, we don't get anything. There is some ambiguity. If you have a term which only has derivatives of the dilaton, that will not give rise to any ODE violating terms. So there's an ambiguity in adding terms which only contain derivatives of the dilaton. So that's why I said this fixes everything almost. But that's a very special kind of term, and in fact, they're known not to appear for the corrections of this. Right, so how long you want me to go on? That's probably trying to wrap things up. So I was going to go through the case, the Riemann square correction at alpha prime. There you can do all the calculations explicitly, but maybe I'll have to skip over that since I already spent getting to this point. And let me maybe summarize instead what you find when you do this. So the Riemann square correction of prime. The idea is now we start from the term. You know that there should be a term that involves the Riemann tensor square. We know that from scattering amplitude, and then we want to determine the rest. And of course, the first step, this is ordinary Riemann tensor, but we argue that it makes more sense to work in terms of the torsional Riemann tensor. So we just replace this with the curly on. And when I reduce that, we get this extra term, which is not going to have ODE, and I have to cancel it somehow. And the only way I can cancel it, it turns out, is to add a term which involves h squared r. And then that produces a term that can cancel this term, but it also produces another term, you're going to cancel that, I need a term that's 4 powers of h. Okay, it's a short calculation, but I'm not going to go through it because it spends so much time already. So let me just tell you the answer. It's just like a couple of lines of calculation. We find that the correction take this form. This is portion for Riemann tensor squared. And then you need a term, as I said, h squared r, h squared ABCD. Again, this 2 h's is 1 and subtracted, times again the torsion for Riemann tensor. And then there's one term that you need, that's 1/3 ABC, h cubed ABC, h squared. It's just 3 h's. With the trace over the last 2 indices, h, so this is like E, and E. Let's keep the antisymmetric see. And this is the answer. Now the point is, the reduction of, it's not that the reduction just gives you no ODD violating terms. What it gives you some ODD violating terms, but they're proportional to the equations of motions. So it gives you some terms proportional to the equations of motion. Right? And that's good enough because if you have terms, generate terms in the effective action proportional to the equation of motion, you can remove them by Fielder definitions. Right? So after doing those Fielder definitions, remember this is in the reduced field. So you do the dimensional reduction, you find that there's some term that violate ODD, and you can do Fielder definitions to get rid of it. And then after that, the reduced theory is ODD. But this is important because you can remove them at this order in alpha prime, but they will come back with higher orders. You won't remove them at the leading order, but then they will generate higher order terms. So this shows that the first order will, in general, mix with all the higher orders. Right? And that's connected to my comment that this first and second alpha prime directions are not independent. Okay, this result, if you write it into a normal Riemann tensor, it agrees to what was found by Simon Cyclin a long time ago. And it's been written in this way before. So this is not something new. But this derivation, we just look at these terms, is by far the quickest way to find this correction. This is you start from knowing this term. It's very quick to find the whole formula. And now you can try to go to higher orders now in prime, and that quickly, for that, the calculations become much longer, but it's still possible to do it.
Without the computer.
Yes, I did it without the computer. I mean, that was kind of the point, because otherwise you don't, it's extremely hard to recognize any structure. You lose track of what you're doing. You get more power to do the calculation, but it's back how you organize the result. Okay, as I said, there's no independent ODD invariant at order alpha prime squared. Instead, what happens when you do these Fielder definitions is that they produce terms at order alpha prime squared, and you have to cancel them somehow. It turns out that to cancel them, you will need this Riemann cubed correction. So the relative coefficient between L2 and L1 and L2 is fixed. As far as ODD is concerned, they're part of the same ODD invariance. So there's only one overall coefficient that's not fixed.
So can I ask?
Yeah.
What would happen if we just started this cube term to the dimensional reduction of this?
You find that there are some terms that you can't cancel.
Yeah.
And then, you know, if you did this calculation, you would find some other terms coming from here and find that they cancel. So it's those terms that we can cancel. Okay, I can try to give you the answer. let me try to write it out, so it's a little bit longer. Let's first write L1 in this slightly weird form. So I would write L1, so I wrote it here, but I would write it in a slightly more complicated form because it's more similar to how the second and third correction look, at least some of the terms are. And I will also introduce some notation that I will use for those. So I'll just write it and then I will explain the notation. All R's are meant to be curved ones. Last term is the same as here. The first two terms are actually the same as these two terms, but then I rewrote, I took half of them and rewrote it in some other more complicated way, which has some similarity with what happens at higher order now, right? I don't know if this is the right thing to do here, but something you can do. So let's explain what these things are. T4 are 2 just means this term, and this T4 means a trace over 2 indices. So we trace over the first 2 indices. Like so. I can write it like this. And then you see this is trace over the first 2 indices and an independent trace over the last 2 indices. The reason for writing this seems a little trivial here, but something like this but more complicated appears at third order in alpha. But there's a T8 transfer, which it's more complicated, but also involves trace of the first and last instance. Okay, but this is some convenient notation. This is defined in the same way, but just with h squared. So h is 1 index contracted, which is 4 indices. This. Okay. Then we have this epsilon things, epsilon 4, prime. I defined 4 minus 4 factorial RAB and to symmetrize these 4 indices. Okay. So this is what you would get if you take 2 epsilon cancers and contract a bunch of indices. That's why it's called epsilon. Here in 10 dimensions, we contract 6 of the indices. Then you get the structure. Okay, finally, this is prime, which means that I don't take all the terms here. I remove all the terms which have a self-contraction. So I remove anything that where the A or B index is sitting here because that's giving me a Ritchie. So I'm removing all the Ritchie terms. So that means that there's actually, in this case, it's only 1 term. Because I have to put CB index there and AB index there, AB index there. So this is actually just minus 4 R AB, CD, R, CB, AB. Not really the same as this, except it's sort of small. Okay. So here it's not really useful to introduce this because it's not independent from the other terms. But it turns out that things like this appear at higher order and all the time. Much more common. And then finally, we have epsilon 5. Define this in more ways. Sorry, should be squared. It's minus 5 factorial. Again, the right something symmetric in upper and lower indices when you anti-symmetrize in all the lower indices or all the upper indices. Same. Okay, so now it's two H's without any interaction. The 5 indices anti-symmetrizing. But again, in this case, this just reduces to something simpler because again, this prime means you don't allow the D or E index to sit here on R. And this just reduces to minus 36 square A, C, D. So again, this is not independent. This is proportional to that in this case. But it's convenient to introduce this notation because now when I write the second correction, it becomes a lot simpler in that notation. After some more calculations. One for the second correction. As I said, it's not independent of this, so the relative coefficient is fixed. Makes this one E6 R cubed. Again, this means you write R cubed, you trace over the first two indices from each factor and the last two indices from each factor. And this relative, this coefficient of 2/3 is fixed relative to the coefficients 3 squared there. E6. Again, there's an H squared. There's a term where you replace one Riemann tensor by H squared. Then another term squared. So you replace these two Riemann tensors by now H, finally, there's a term 6 H squared square. Okay, so that's the term where you replace two of the Riemann tensors. You replace one of the Riemann tensors there by squared, or replace two of them with squared with that term. And those are all the terms where you have the structure to trace over first two indices and trace over the last two indices. Then you have a bunch of other terms. In particular, you have the epsilon type terms. Then the symmetrization in indices. Epsilon 6 R cubed. Minus 1/2 7 prime. So there's one more thing. What we have to do is I put a hat. I will explain these. 1.6. Square again, this is the same as this term, except that it is Riemann tensor by root of H. Okay, these are the terms that have a structure that's very similar to what I wrote there, and it's also very similar to a structure that appears without the prime cube. With this, in that case, T8 and E8 and E9. But then there's a bunch of other terms over. And they can be written in this form. They can be written in a huge number of ways. Simplest way I found to write them. That's some sort of basic structure. This. the three more terms. It's like form is obviously not that important. I just want to write it down and specify that it's completely explicit. No, it's not. It's like with all these special meanings. And the last term. Again, involves this H cubed combination that I found. And now it's not H times H cubed that we have, or it's H cubed squared, so that is 6 H's. Okay, so that's the full answer. Okay, it's not very simple, so I didn't tell you what this hat means. This hat means means to remove the terms where there's no contraction between the two H's or all the indices are contracted. This would be all the indices on the H contracted. There will be terms like that coming from x17 and x17. This happens for us to remove those terms. There will also be terms where there's no contraction between these two H's. We also remove those terms. Okay. You could have explicitly done it by these are just that happen here. Okay, so you see there's some similarities. There's this the Riemann cubed term has the same form. Or alpha prime essentially the same form, but the trace of the first two indices. The last two indices over alpha prime over alpha prime squared, and it turns out again over alpha prime cubed. There's a term H squared, well, where you replace one of the Riemann lines with respect to the square again, but if it's first order, second order, and also the third order. Then also these terms here also at all those order. Well, at the first order it was ambiguous. I could put that term in or I couldn't. So the coefficient is ambiguous at the first order. But it appears in the second order. At least I can write it in a way where it appears. And also at the third order now. I didn't write that result. This is a bit more complicated. It's not, this is about 1415 terms if I write it in this way. At the next order now for prime. But I only worked out the result up to the fifth order in fields there. So it starts at the fourth order, the Riemann to the fourth, and it turns to the fifth order in fields. And if you write it in this kind of way, you can get it down to like 30, 35 terms. Which compared to the 200 something terms, of course, that was all the terms, but there's no reason to think that the higher order terms will be simpler. For example, if you look at this result, there's very few higher order terms. These terms, almost everything stops at the fourth order. These extra terms that are written in terms of H, they all have 4 H's. There's only this term, which is the sixth order in fields, and there's this term, which is fifth order. Everything else is fourth order. Whereas you can write tons of terms that are fifth and well, yeah, also sixth order. You can write lots more combinations of H's. All those terms you can get rid of. You can write. Whether this is the best way to write it, I'm not sure. Yeah.
So Garusi did the alpha prime squared
So
in his computer as well.
yeah, so he did calculate the alpha prime squared result. He didn't write it in this way, but you can show that this result matches. So he wrote it in terms of the ordinary Riemann tensor and just didn't write any of this epsilon structures, just expanded everything up. But you can show that up to field definition matches us. But actually, he, again, you have to also include the first order correction. So he got that result by using a more complicated Lagrange than the first one. So his first order Lagrange was more complicated, but actually the second order Lagrange agrees with what we have. Whatever. So actually, it turns out that this fielder definition we can also simplify the first order. So both the first, second order. So it matches completely what he has, and it matches with. So he also checked with scattering amplitudes up to 4 points. So this matches with the 4-point scattering amplitude calculation. So that fixes the coefficient of most of these terms, but doesn't fix this one. Yeah, so it agrees with everything it's known. It's reasonably simple. Certainly, if you compare it to other ways of writing it. I mean, before that was relatively recently, that was like 6 months ago, where he found a simpler form to write it. Before that, they were much more complicated. It's very easy to write something much complicated. It's very hard to write. Essentially, it's possible to try to play around with it. Seems impossible to write anything. Now, these terms have sort of a structure that seems to repeat at 5 orders. For these terms, it's less clear. But actually, it turns out that you can write the result of the next order, alpha prime cubed. You will also find, in a certain way of writing the result, you will also find a term like this appearing, but with 2 extra derivatives sprinkled on the edges. But again, you find the structure with h squared and they symmetrize them for derivatives now for indices. And again, multiply with this kind of combination. Just the 2 extra derivatives sprinkled on. And then you find some other terms like these ones, some extra terms, which don't have a very clear structure. They have higher powers, h and derivative of h. But they cannot, it seems like it cannot be written in terms of this just tracing over indices and antecedent tracing in indices. There's no answer. Right, so I think I'll end there. Thank you.
Like if I dimensionally reduce this, so I get some equilibrium terms.
Yes.
That I need to push to the next order.
Yeah, so in this calculation, I also kept track of the equation of movement terms. Again, the same thing happens that when you reduce this, you get something that will be derivative only of the equation of movement terms. And then you can remove those again in the field definition, and that will again produce terms of higher order.
So you push it to the fourth order, like
Yeah.
alpha prime 4.
Right.
Then does it mean that alpha prime 4, like the overall coefficient, is kind of related to the first correction and second correction?
No, not the overall. There will be terms.
Okay, not overall. But
Well, it could be if there's no other correction of the fourth order, but that's not really known. But there will also be terms generated as the third order now. And those are different from the terms that I talked about originally, which are proportional to say 3. There will also be other terms generated from this example, which are part of the correction that started with the Greenland square. There will be other terms related to that, or they will obviously not be proportional to say 3 because there's no system here. But on top of that, there will be an independent variant of the third order, which is proportional to say.
and also, does type 2 Sura as alpha cubic, alpha prime to the 4th correction? If they do, then that order, they are different, right, compared to the Bosonic case. Because in the Bosonic case, the 4th order receives correction from the 2nd order, but in the type 2, there's no 2nd order terms.
Yeah, it would certainly be different. Yeah, it would certainly be different. I mean,
But-
already at the cubic order, as I said, there will be a difference because there will be terms coming from this by mixing, because you have to do the Gilbert definitions of order alpha prime, that will generate things that order alpha prime square, alpha prime cube, and so on. So it will already generate terms of order alpha prime cube. So there's already a difference between the Bosonic string and the type 2 string and order alpha prime. Q. Whether the type 2 string has a correction interval around 1/4, I don't know off the top of my head. I don't think so. That would be
So you said like,
Riemann to the 5th, but I don't think so. Probably Riemann to the 6th.
sorry, you won't quite understand. So, like you said, even like in the boson case, the alpha point cubic level, they're different to the type 2?
Yeah.
Okay.
Because some terms will be part of this invariant discourse is Riemann squared. Some terms will be proportional to set of 3. So there will be terms proportional to set of 3, and there will be terms not proportional to set of 3. What was the bosonic string? Whereas for the superstring, everything will be proportional to set of.
So you're reducing on D dimensions. If you just reduced on one dimension, could you say, draw all the conclusions that you did, like O1, is that enough to say something? So you know, there seems to be some sweet spots. So if you reduce too much, then you destroy lots of the structures.
I kept the arbitrary there, but essentially very little different. I don't think if you take D as 1, well, that corresponds to the case that Caruso considered. Caruso considered all the terms. So it's possible that you would miss something here, but
So you're relying on some kind of universal structure because you have it works for any D.
yeah.
So what about the, so you said you could throw away the scalars because you cannot form some good invariants for those? Or?
No, you can include the scalars and but things become much more complicated.
Okay,
The
so
point
it's
was that
incomplete in that sense.
Right.
So it's incomplete in that sense.
well, no, this answer is not, this high dimensional answer is not incomplete. But I looked at it, I did incomplete set of terms in lower dimensions to fix this. I threw away a lot of the terms in the reduced here and just looked at some of the terms, but it was enough to look at those terms to fix all the coefficients.
Right, but you're saying there are more terms.
In the reduced area, yeah, there are tons of terms. You could reduce, and if you want the full reduced action, then you have to keep all the scalars and everything. That's would be an enormous expression. And then you can check the full will be the symmetry. Here I just impose the necessary conditions. But the point for me is I'm interested in the high dimensional theory. I'm not interested in the lower dimensional reduced. Where anyway is throwing away a bunch of things because I'm dimensionally reduced, so it's not a string effective action in the lower dimension, it's just a reduction. I'm already throwing things. So for me, the reduction is just a tool so that I can get the ODD symmetry, so that I can have a constraint, an indirect constraint on the higher dimension.
So in the next step, we will take all the corrected transformations of this in the previous section, and also the first term in the L3, like this, 4. Then
If you want to push the same correction to the next order, yeah, then you would have to include all the corrections. First from the field definitions of the field definition of the lowest order alpha prime that will generate things of this order, which have already taken care of. But it will also generate things to cubic order.
and you take it with and then you take also the factor for the term at leading order, or do you create?
Yes, but it will be a different structure of our report, but there will be a different report term, they will have different structure. But that's not being completely worked out. It will be very complicated because now there's a lot of mixing. Because corrections in the field definition of this, field definitions of this order, which are quadratic in alpha prime, you have to plug into the first order correction, such that it will generate an enormous amount of terms.
But in theory, it would happen that if you're calculating the next order direction, the L3, that you are at just some part that by itself is only required, but maybe it's not the full action. If the overall action has some, let's say, different components which are by themselves OBD invariant, then if you use some generative method, it's possible that you just pick out one of them.
They can be different ODD invariants. In fact, at the next order, there will be an independent ODD invariant appearing in the next order, which is the one according to the set of three. So if you try to do this and you include some Riemann to the fourth term of that structure, the coefficient of that will not be fixed because it's part of another invariant which starts at that order. That should be the only other one that's at order.
So,
Yeah, it's not fully known, this function.
so at prime cubic, there are two different ODE structures, or like one is 3, 2 is 3?
Yes, but one set of terms is really part of what starts with Riemann squared. But as far as ODE, one invariant is Riemann squared plus Riemann cubed plus Riemann to the fourth. This is one single invariant. That's not coefficient. Then there will be some other invariant which starts with this a specific Riemann to the fourth. Terms above the period. And this will have some other, I noticed that the fourth will have also, but this will be an independent. But to this order, up to order Riemann cubed. And there will only be two elements, so it equals.
You're also using this method before the deltic corrections with the chain sounds.
Yeah, in RESTful you can also do that for upstream, but you have to modify things a little bit because there you have to modify also the gauge transformations for the B field. And also one thing that I used here is that again I use the symmetry on the B going to minus B, which means that you can only have the even power of the H's here. That would not be true there, so it's a little bit more complicated. But I don't see any reason why you couldn't apply the same ideals that I didn't try to do.
Do we have some other questions? And so before we thank Linus again,